The next topic is we derive the PDE. We are trying to solve the PDE with the boundary conditions. We solve the steady state when the temperature is now depending on the time. But now we are interested in how about the transit, how about the temperature from the beginning to the equilibrium, how the temperature change as function of time. So we are trying to solve the in-transit temperature distribution as function of time and space. And to solve such PDEs, we will use a traditional powerful method called the separation of variable method. Okay, so the separation of variables method. It's a very powerful method to solve PDEs. And what this method is, as its name, the separation of variables that assume u function u of x of t can be separated as a function, a product of one function as only as function of space, another function only as function of time, so that you can separate these two variables in your ux of t. So uxt can be separated, some function only as function of x, the other function only as function of t, and a product of them. Then what this separation of variable method apply to? What kind of problem we can use the separation of variables? So the SOV, separation of variables, can be applied directly to linear homogeneous problem with homogeneous boundary conditions. Okay, so of course we will talk about some other examples which is indirectly can use separation of variables which doesn't satisfy for the homogeneous problem with homogeneous boundary conditions. But as a simple example to introduce this method, we will follow the traditional SOV can be applied directly to the linear homogeneous problem with homogeneous boundary conditions. Then after our ux of t separate to fx and gt, and with homogeneous boundary conditions, this fx and gt will be two homogeneous ODEs with homogeneous boundary conditions. Okay, so it become from the PVE transfer to the ODE, and it will be a homogeneous ODE with homogeneous boundary conditions, and you can solve it by a traditional means of the ODE we introduced before. And if this is a second order ODE, for example, fx second order, homogeneous ODE with homogeneous boundary conditions, it will fall into the category of the Sturm-Liouville problem site. Okay, so if the original ODE second order with homogeneous boundary conditions, then it becomes a Sturm-Liouville problem. And when they introduce Sturm-Liouville problem types, we show that the final solution will be orthogonal basis set, right? So it will generate the orthogonal eigenfunctions as solutions. And since our PDE is a linear PDE, then the final solution will be a linear combination of individual solutions, right? So the PDE is linear. That means our final solution is formed as a linear combination of individual solutions. And it will be, since this involves some Sturm-Liouville type problem, it involves orthogonal eigenfunctions, which is infinity orthogonal eigenfunctions. That means the individual solution will be infinite, right? So it will be a linear combination of individual solutions, and in the end will be an infinite series. For example, you will involve some Fourier series, such as sine, cosine functions, right? And how you solve it, of course, we need to apply the boundary conditions to solve the linear combination part that's coefficient. So you will apply boundary conditions or initial conditions, whatever the condition you didn't use before to solve the steady heat distribution, then the time is infinite. You will apply some other boundary conditions or initial conditions to determine the coefficient of infinite series. Okay, so this is the separation of variable method. You will separate first to be function, a product of two function. The two function will be only depending on either x or t. Then this, since this SOV can apply for homogeneous PDE with homogeneous boundary condition, then after the separation, this fx and gt will become a homogeneous ODE with homogeneous boundary conditions. If one of them is a second order homogeneous ODE with homogeneous boundary conditions, it becomes a Sturm-Liouville type problem. Then the solution will become orthogonal basis sites. And the UPDE will be a linear combination. The solution of the PDE will be a linear combination of those individual solutions of the infinite series, such as Fourier series, sine, cosine form. Then you will apply some other boundary condition or initial boundary conditions, initial conditions to determine the coefficient of those infinite series. And since the solution will be an infinite series type, you will need the computer program to help you to evaluate what your solution look like in the end. So you couldn't solve it by hand, okay? Then we will use examples to elucidate this separation of variable method, okay?